Hello everyone, welcome to Deterministic Optimization. Today we're going to start a new module on large-scale optimization with a specific focus on a new algorithm called Danzig-Wolf decomposition, and this is the first lesson. So in this module, we're going to learn how to discover special structures of large-scale optimization problems, and this is a universal scheme and very important idea for solving large-scale optimization, meaning to discover special structures and to design new decomposition algorithm to exploit some special structures of the large-scale optimization problem. So this lesson, we're going to motivate the Danzig-Wolf decomposition algorithm by an example. And from this example, we'll formulate a large-scale optimization problem, and we'll identify some special structures that are very important to exploit. So here is the example. Consider a large company that comprises n subsidiary units. So it's a large company that has smaller companies or units under it. And each subsidiary unit, I, has its own objective. And their objective is their profit. So they want to maximize their profit by planning their own production and subject to its own constraints. So you can think about each subsidiary unit or subunit is a small company by itself, and it has its own objective, has own internal constraint. So for each subunit, they have to make their own decisions. We call this decision xi for the ith unit. And this xi is a vector decision variable. It can be how much to produce for that subunit, how much to store, how much to sell, etc. So this is whatever decision that subunit I needs to make for their daily operation. Also, this subunit has its own local constraints. We write it in the most general form as linear, standard form linear constraints as ai xi equals bi. Ai is a matrix, xi is the decision vector variable, bi is a vector, right-hand side, and xi being non-negative. And this kind of local constraints can be anything that the subsidiary unit needs to consider. For example, they need to satisfy their own customer demand, and they have their own production, capability limits, and so on. So each subunit has its own decision and has its own constraints. Of course, it also has its own profit function. And all units share a common resource. So the units are not completely independent of each other. They are constrained by a common resource. For example, this resource can be monetary budget or total machine time or some other resources that have to be shared by all the units. And this monetary budget or other budget constraint or resource constraint is the coupling between the different units. The large company or the holding company can impose certain such constraints. So the large company wants to maximize the total profit as the sum of the subunits' profits, respecting their local constraints and respecting the total budget constraint. So this is a pretty general and typical operational problem in a large organization, and that is composed of smaller units, semi-autonomous units that have their own decisions to make and have their own autonomy to make their decision, but the units are constrained together by certain common constraints. So this overall problem can be modeled in the following picture. We have a holding company that has its overall objective of maximizing certain function, and for example, profit or sales, whatever function that the company puts as its maximization objective. And it has subunits there are n subunits here. Each subunit has its own decisions and constraints, and they're all coupled together by this common coupling constraint that says T1x1 plus T2x2 all the way to Tn xn equals B0. So this common constraint, again, is a general linear equality or inequality constraint. It doesn't have to be equality, can be inequality, but it's the linear constraint that has all the variables from all the units, whereas the subunits here only has its own variables. So we can formulate this overall problem in the following way here. So we want to maximize the total objective here as a sum of individual units objective, subject to the coupling constraint, right? These T's are matrices, and Xi's are the decision of the ith unit. And then we have n constraints, set of constraints for each company. So this is the overall problem. If you consider the subunit can be, number n of the subunits can be pretty large for a large company, and also each unit's own decision, xi, could be a high-dimensional decision variable. So this overall problem is a large-scale optimization problem. It's not just one unit, it's n copies of that, plus some coupling constraint. So the question is, how do we solve this large-scale optimization problem? And this problem by itself has an intrinsic special structure. We want to identify that special structure and exploit it. So the way to identify or discover special structure, here we're going to introduce an interesting way or useful way is to write everything in a matrix form. So if we write it in a matrix form, the previous constraints, then we have one row. This is a row of block matrices, T1 to Tn, multiplied with x1 to xn. And this row times this column equals B0. Right? That's exactly the coupling constraints. And then we have this for each subunit. Right? We'll have a row of block matrices, where the first one for the second row here, the first one is A1, and then all the other blocks here are 0 blocks matrices. So we're not writing anything. These blanks here means they're all zeros. So if you multiply this row with this column, you get A1 times x1 equals B1. So that's exactly the linear constraints for unit 1. And so on. For unit 2, we'll have A2 times x2 equals B2, and so on, all the way to AN times xn equals Bn. So once we have this large matrix composed of smaller block matrices, then we can see that this is a special structure. We have one row of block matrices, and then the diagonals here are matrices for each unit, and all the other parts are 0. Okay, so this is the special structure, and this special structure is very important. It's called block angular structure, because every matrix or every element here is a block matrix. It's not just a scalar number. It can be a scalar number, but it can be also a matrix here. And then the angular means the non-zero matrices are only on the diagonal in the lower part of the matrix, so on the angular side. So this is called block angular structure, and it's a very important structure that appears a lot in optimization, large-scale optimization, especially in this context. We have subunits here, and they all couple together. Okay, so how to exploit this special structure? We're going to call this coupling constraint here, T1x1, T2x2, all the way to Tn xn, sum over equal to B0. We call this complicating constraints. Because if we don't have such constraint, if we don't have the coupling or complicating constraint, then all the units are essentially separated or decoupled. There's not any coupling constraint linking different subunits. Then each unit is a much smaller problem by itself. So if we can somehow get rid of the complicating constraint, then the whole problem becomes decoupled into n separated and smaller problems. So this is the special structure this is due to the spatial structure of the problem. And this leads to a very important algorithmic idea called distributed optimization and coordination. So we still want to solve the large scale problem involving n small units and the coupling constraint, but the way to solve that is to somehow get rid of the coupling constraint first. We're going to get into exactly how to do that. We don't really throw away the coupling constraint, but we need to deal with it in a way that it disappears almost. And then let each subunit solve its own problem for its own decision, subject to their own constraint. And these subunits can solve their own problem in parallel or in a distributed fashion. So there is no central controller, or there is no central planner to make that decision for each unit. Each unit can do whatever fit to their own problem. And then all the subunits need to coordinate. So after their individual optimization, they're going to coordinate so that the coupling constraint will be taken account for. So that is the so-called coordination and distributed optimization. There is a distributed optimization phase that each unit solves its own problem, and then there's coordination phase so that the coupling, linking, or complicating constraint can be taken care of. Okay, so summarize, we have learned important structure in large-scale optimization called block angular structure, and this arises naturally in this situation of individual units coupled together in a large organization. And we also introduced the idea of coordination and distributed optimization, and we outlined what is the rough steps of that. So in the next lecture, we're going to go into details to describe an algorithm that can deal with this kind of block angular structure. And the algorithm actually is implementing the coordination and distributed optimization, although it, in the first it's hard to see it, as we will introduce next lecture. That's it for this one. Thank you.